This section we're just going to take a look at some other graphs and see what some differences are between these and the ones that I'm expecting you to make. Now, first of all, this is a graph that you're going to make in your portfolio. It's called a multiple bar graph. This part over here, this is called a legend. Most of the time I tell you not to have a legend when you make any graph because it's not convenient for the person who's reading the graph to try to match some little colored box to a color on the graph. However, when you're displaying more than one set of data and comparing it on a graph, that's the only time that a legend is proper. And here we're comparing the blue bars stand for 1970 to 2000, so having them side by side, we have to identify which one is which, and a legend, like I said, is appropriate. We can do a multiple line graph, same sort of idea. Notice that the lines here, when you look at the legend, they're not just identifiable by color, but each line has a different shape on it. That's most helpful when you're having to do something in, say, black and white, and the different colors might not come through. Stack plots are where you literally stack one set of data on top of another. They're notoriously difficult to read. Again, we have legends because we're showing a whole bunch of different kinds of data in one graph. The one on the left, it doesn't have any numbers. And what you have to understand is if I want to examine how much moderate alcohol was involved in automobile fatalities in 1988, I have to examine that wedge. So I'd have to extend it over to the side and try to figure out how tall is that wedge. The magenta and the yellow color, they don't go all the way to the bottom. They just go to where the top of the data below them ends. That's why it's called stacked. Literally, your data is stacked on top of each other. Over on the right, the stack plots there, they take away the problem you have with trying to identify dollar amounts. The dollar amounts are displayed, but what it does is it also distracts. I have the dollar amounts, but who wants to read that many different dollar amounts? All I can really tell from that graph is that bottom blue bar is growing immensely. If any of those other colors are growing, I'm not sure I'm interested enough to check the differences in the dollar amounts there to see if any of these little wedges are growing or not. So stack plots, you got to be careful. Sometimes it might be better to use a bunch of smaller graphs that are clearer in the point you're trying to make. There's two kinds of graphs that use maps. The one on the left is a geographical data map, and what that does is it uses the actual boundaries of the map to make the groups, and then you'll average whatever data it is that you were collecting from these different regions. Now, the map that we have here is of the United States, so we have one number that represents the average for all of Texas, for all of Tennessee, or for all of Alaska. You can use other maps. You can do it with countries, if you wanted to do a whole world map, or if you wanted to do it with a continent. You could look at even a map of just a state that has the boundaries by county. The feature here is that you are using the boundaries that came with the map to group your data together. The map on the right, the contour map, you can see the boundaries of the United States in the background, but the colors are joined by a common feature. Each color represents a different temperature region. So the 20s, every place that the 20s is expected to occur is colored that bright blue. The light blue is where we're going to experience the 30s. The 40s are all beige, and it crosses state lines. It dissects states, but state lines don't matter except to just make it so that you can identify which temperate region you're going to be in. But otherwise, the boundaries of the data, ignore the boundaries of the map. The boundaries of the data, they're connected by a common feature. Three-dimensional graphs. The one on the left is a true three-dimensional graph, which means I have data that's being displayed across the x-axis, up and down on the y-axis, and this would be a z-axis. I'm comparing a whole bunch of different places. That's true three-dimensional data because I have data that's displayed in 3 different directions. The graph on the right, I only have grades and frequencies as part of my data. The fact that I'm using a thickness at all, that's just to make it so, I don't know, maybe it looks cooler or it looks more fancy, but it's really only 2-dimensional data, which is not an appropriate use of a 3-dimensional graph. If I wanted to display graphs in a 3-dimensional grade, I could possibly have maybe the grade distributions for 2 or 3 different classes that would come out here and actually add to the thickness. But otherwise, you should really kind of stay away from using a 3-dimensional graph unless you actually want to show 3 different sets of data combined. This is a good example of a combination graph. You could do a combination graph that again could get so busy that it's not really going to be helpful. This one though is a good display. If you look just at the basic line chart that they're trying to display here, it shows the number of women in the Summer Olympics that were competing. So from left to right, you can see the sharp increase, starting in the 70s and 80s and on into the 90s of the number of women who competed in the Summer Olympics. And that's a pretty good understandable display of that. But not only do we look at the number of women, if you look at each one of the points, the over-exaggerated points that the line graph is plotted on, each point is actually a pie chart. Because think about it. The number of people who are participated in the Olympics from year to year has probably increased. Probably even the number of countries. So the pie chart shows the percentage of the participants that are women. So if you see the pink part of the pie chart growing, not only does the sheer number of women appear to be growing, but the percentage of women has grown from 1900 and 1904 being somewhere between 1 and 1.5% to now 42% of the participants in the Summer Olympics are women. Part of it that's not really part of the combination, but it's just an added extra feature here. If you look below the x-axis, that tells you how many games there are for women to participate in. So again, instead of just having 2 or 3 games that would include women, we're up to almost 140 games in the Summer Olympics that women can compete in. Pictographs are usually trying to distort or hide information. This pictograph on the left has a whole lot of artwork happening up here. Look at all this stuff that has absolutely nothing to do with what this graph is trying to show you. And not only do we have the lovely artwork, we have these 3-dimensional bars that make it look like little stair steps. And they are 1, 2, 3, 4, 5, 6, 7, 8, 9. Everything's going nice and slow and steady. And all that distracts you from the story that's happening on the x-axis. When you have an x-axis and you have tick marks, or you have a bunch of bars above it, these tick marks on the x-axis are supposed to be equally spaced apart. Equally spaced means that the distance between the two numbers should be equally spaced. So if I examine the x-axis down here, we go from 1804 to 1927. That's something like 123 years, right? So that scale from one tick mark to the next was 123 years. Now we go from 1927 to 1960. 1927 to 1960. Isn't that something like 33 years? 123 years between the first step and the second, and now it's only 33 years between the second step and the third. And what happens when we get here? That's only 14 years. You can't do that. If you have an x-axis, if you start counting by 123s, you got to count each tick mark as 123 apart. You can't scale your graph by the y-axis. If you do, it's a lie. Over on the right, there's a lot of graphs that are made of pictures instead of bars. The problem with that is you can't tell how much of that picture is embellishment and how much of it is actually supposed to tell you the difference between two things. In this case, I'm looking at the cigarette smoke. My cigarettes on this graph are all different sizes, but the smoke stays the same. Because the smoke never gets smaller or longer. Because the smoke part is always the same, it makes me wonder, does the smoke actually count? Or is that just fancy artwork like the Kumbaya people over here? Is that just to make a point that the cigarettes are lit and that's how they're getting shorter? Or is the number of women almost 35% here instead of 25? I'm not sure, and unless we call the guy who made the graph, I'm not sure we'll ever know for sure. We just have to kind of guess. Another problem with pictures, if this was like our national debt before, and I say our national debt has doubled, if I double the length and I double the height of a picture and keep it square, this picture is not twice as big, it's 4 times as big. It's very difficult to double the size of a square, especially since we're talking about area. You have to figure out how much area would be twice as big. Otherwise, this is an exaggeration if you were talking about doubling the original. If you just took a quick glance at that graph, and I asked you, does it appear that men make a lot more than women or a little more than women? You would probably say in your gut it's a lot. Because this bar on the left looks like 2 or 3 times this bar on the right. Check it out. That's the same graph. Here, my y-axis starts at 0. Over here, my y-axis starts at 300. So, essentially, we've taken this graph on the right and we've cut it off and just shown the top part. The math is still the same. The women come up to a little bit above 330. The men come up to almost 380. Nothing wrong with that. It's just that if I only show the graph from 300 and above, I'm ignoring all this part that was similar. And if I ignore the part that's similar, I'm ignoring a large part of the area. this isn't 2 or 3 times as much as this. It's actually only this much more. And one last visual distortion. It takes you a minute to digest this, but these two graphs show exactly the same data. Exactly the same data. Let me say it again. Exactly the same data. On the right, you're talking about college tuition costs. If you follow the pink or you follow the blue, nowhere along either of those lines do you see tuition go down. None of those bars get shorter. So, if the pink bars are the same as the pink line and the blue bars are the same as the blue line, how come the lines go up and down when the bars only increase? Because this graph shows rate of increase. Rate of increase. Let's just look at the blue line for a minute. The blue line here in 2000 to 2001 had a 4% increase. So that means tuition went up 4% from the year before. If I look at 2001 to 2002, tuition rose by 8%. So that shows that increase is not the fact that the tuition went up, but that it went up by more than it did last year. Now what happens when we get to 2002 to 2003? Tuition still went up, but it only went up by 4%. So it increased, but it increased by less than it did last year. So the rises and falls, the rises and falls have nothing to do with costs ever going down. A fall just means it didn't go up by as much as it did the year before.